competent question. So I got some point right system. Okay. Take your time with this. Try to rush. If he's got there at 4 o'clock and you get there to his office, then just put it on. Send it around my desk. And then in the morning, I'll grab it and give it to Bill. But make sure you don't leave those steps. Make sure everyone writes the copies on the back of the desk. Every question and also scores like this. And then, like, either your PTA, I know everything is restricted to PTAs, and you have to go back and say, and there's 2 problems wrong with it. So, on the answers. So if you happen to, you might notice it. I noticed it when I was grading. Joe gets wrong and wrong. This one is Boolean on the online test. Just point that out and say this one goes on.
No, I removed it. I'm doing it via Wi-Fi.
It will work?
No,
No, I mean the Wi-Fi will work?
yeah, I connected it through my Uconnect.
Yeah.
Through my account, so it should work.
Write it down and tell them these 2 are right.
All right.
Don't write down.
Let's start.
It's really Boolean.
So we were talking about flows last time, if you remember. And this is a brief summary of the things we talked about. Not all of them, but at least some of them.
No, it's right here.
We talked about flows being defined in a directed graph where you have a source and a sink as 2 special vertices in the graph. We have a notion of capacity on an edge. Again, you can think about the diameter of a pipe. You can think of flow on the edge as water going through the pipe. We defined a notion of a value of flow as basically the flow coming out of the source, or as we will see, conversely, the flow coming into the sink. And we defined the notion of a cut as the total capacity of edges going from one side of the cut to the other, where a cut is a partition of the vertex into 2 pieces, one piece containing the source and one piece containing the sink. So in fact, let me write that up here. We talked about constraints on this flow. There are rules that the flow has to satisfy, otherwise this problem is not very interesting. But in particular, you can't overfill a pipe, so the flow has to be less than the capacity. You can't produce and create water from nothing except at the source and sink. So for any vertex that's not a source or sink, what goes in must come out. And that's the equation. And so once we describe this basic setup, right, with these concepts, we then started asking, okay, what can we say about these notions and how might we work with them in some way? And of course, the first question we asked was, so the problem 1 was, find flow that maximizes. So find the max flow in a graph. Right. We also had a separate problem, which was find A comma B. Again, S belonged to A, T belonged to B, which we call an ST cut, such that is minimized, right? And of course, the main that finding the maximum flow in a graph is equivalent to looking at a structural feature of the graph, namely a cut that has the smallest bottom. And again, this makes intuitive sense that if you're going to push something through, the smallest choke point is going to constrain how much you can push through, since you're not allowed to produce or delete things except for certain things. But of course, the intuition is not the same thing as the proof. And so it was very easy to see that the max flow is less than or equal to the value of a min cut. In particular, we showed that the value of any flow is less than or equal to the value of any cut. Right? So in particular, the max flow, if any flow is less than any cut, the max flow has to be less than the min cut. And the other part of this was saying that they're in fact equal. And we argued that the way to show this would be to construct a flow and an associated cut that has the same value, because if you did that, you would be showing that they matched. And we had some discussion about this and said, okay, this in fact would be a proof that the max flow is equal to the mean cut. And so we presented an algorithm last time based on this notion of augmenting paths. So we talked about the Ford-Fulkerson algorithm. Okay, this is all review, so this is all stuff we covered. And in order to implement the Ford-Fulkerson algorithm, we said, okay, let's find a path from source to sink and augment along that path, which basically means find a path from source to sink, find the bottleneck edge along the path that constrains the amount of flow you can push that flow. Update the graph, and this is the key point that made the algorithm work. We update the graph to construct this residual graph, right? So I'm going to add this extra notion of residual graph, which we talked about last time. Right? And if you recall, the idea of a residual graph was that if you have an edge from V to W and you push F units of flow on it, of course its capacity effectively reduces to C minus F, so that edge is still there. But what you added is this back edge of value F, of capacity F, not value, of capacity F. Because you're saying, I can now actually push backwards up to flow F if I want to change my mind. And so this process allows you to maintain in this residual graph information about the aggregate flow you've pushed through so far in this sort of memoryless way, this extra information. And this is consistent in that you can keep doing this, and at any point in time, the sum of the capacities along the forward edge and the back edge will always be equal to C. That's the invariant you're meaning. Okay. So once we decided on the residual graph, we described the Ford-Fulkerson algorithm that basically said keep running, and I think I have it right here. While an augmenting path exists in the residual graph, augment and update the residual graph. And we walked through one example where we showed that we in fact can, in some sense, change our mind if we have a bad path and get it next. And so at some point this algorithm will stop, it'll give you a flow value. And the question really is this a max flow? And the way to, yes?
So a question, so does augmenting path just mean somewhere where flow can continue?
From source to sink.
Okay.
That's right. Any path from source to sink that has capacity on it to push more flow is an augmenting path. We didn't say anything about what kind of paths these are. We don't care. That's the beauty of this algorithm. It doesn't care what paths these are. As long as there's some path, just augment along. How would you find a path, by the way, from source to sink in a directed graph? What's the easiest way you might go about doing that? Or check if such a path exists.
Like breadth first?
Yeah. BFS would be fine. Just find it, just go through and find it. Okay. The question then became, when this algorithm stopped, as it will stop, does it give us the correct answer? Has it maximized the flow? And the only way we can prove, or we know how to prove this, is by in fact showing that there is a cut of the same value. Because at that point we know it's guaranteed to be the maximum. You couldn't have got a better flow, because there was a cut in that value. And that's what we haven't proved yet. So what we want to show first of all is that in fact this algorithm is optimal. That it will give you a cut of the same value. Okay. Any questions so far? So this is all just review from last time. Is all clear? Okay, let's move on. So here's what we're going to do. So let's say we stop at some point. So we stop. So the FF algorithm has stopped. Why does the algorithm stop? What is the condition for this algorithm to stop running? So we said this algorithm basically is keep doing something till something happens, right? What is the something that we do till something happens? And what is the something that stops it?
Capacity goes to 0.
Where?
Source to sink.
What is the source to sink capacity?
I mean, how much flow we can pass on. We cannot pass any more flow than we have to start.
Why can you not pass any more flow? Because?
We have augmented some path. We have cut some paths.
Right, but what is preventing you now in this graph that you have from finding an augmenting path?
Some bottlenecks, which means there are some edges which cannot. There is no path essentially.
There is no path from source to sink. So when the Ford-Fulkerson algorithm stops, this means that there is no path from S to T in residual graph. Not in the original graph, of course, but in the residual graph. So why would that, what does your graph look like when this is happening? Remember in the residual graph, as you're pushing flow forwards, you're adding an edge backwards, right? So if you think of what your graph looks like, so we have the source here, which is S, we have this sink here, T, and we have this entire graph in the middle here, right? As you add these backwards edges, what do you think is happening? We're adding these backwards edges here. So essentially what's going to look like is something like this, right? And since this is a directed graph, there basically is no way to get from the source to the sink anymore, because all your edges have flipped backwards by pushing flow forwards. Okay? And again, they may not be this nice line, I just drew it that way, but it could be some other edges here, there could be some other edges here, and of course there could be still some edges going forward here, coming out of the source even, there could be some edges going into the sink, there could be all kinds of things happening. But there's no way to get from the source to the sink. That's the point. And that's why the algorithm stops. Okay. So let me now define a cut. A cut computed from this flow, and I will then tell you some properties of the cut. So the cut I'm going to define as, of course, it's going to be a set A comma B. And I'm going to say A equals First of all, is this a valid ST cut?
Yes.
What is a valid ST cut?
It has S on one side and T on the other.
Why is this a valid ST cut?
Because we can't reach T from S.
Therefore, S must be in A and T must be in B. Okay. The claim I'm going to make, so let's say the forward calculus algorithm stops and the value it gives us some F star. The claim I'm going to show you now is that okay? I'm going to show you that the capacity of this cut that I just defined is equal to the value of the flow that defined it. Therefore proving that this flow is optimal. So before I go ahead and prove this, hopefully you believe that if in fact I were to prove this, I'm done. Right? I constructed a cut, it's a valid ST cut. I know that max flow is less than equal to any flow is less than equal to any cut, and I'm going to show that these two are in fact equal. So I've matched them. Yes?
Are we proving that the algorithm will stop at some point, or are we just assuming that it will?
We are assuming that it stops. I have not yet proven that it stops. This is a very good point. Let us assume for now that it in fact does stop, and in a few seconds I will prove to you that it does stop. Okay, it stops in a finite amount of time. It's actually not that good amount of time, but it does stop, and I can prove it. For as long as your capacities are integers, but yeah. All right. So let's try to prove this claim. So what is the definition of this cut value? It is the sum of the capacities of edges going from A to B, not counting the edges going back from B to A. Right? Okay. So let me make a subsidiary claim. So let's sort of look at the picture here. So we have a picture that looks like this. This is my set A, and this is my set B. And I have a bunch of edges going forward and maybe some edges going backward. Right? First of all, I will argue that the max flow, the flow F star, equals to the total flow, net flow going across the set. In other words, the flow coming out of S is equal to the flow going across the set. So I'm going to first write this, that F star, the value of F star, is equal to the sum over all, let's see, U belong to A, V belonging to B, F star U going to V, minus the sum of all U going to A, V belong to B, F star, B. Of course, my summation is a little rough. I don't mean every pair, I mean every pair that actually has an edge between them. Right, so this is the flow, by definition. Because of conservation of flow, this is in fact a flow going out of S, it's a flow going into T. Because once you push into T, there's nowhere else for it to go. It has to go in. And again, you can prove this fact. I'm saying this just casually, but you can actually prove that this in fact equals to the flow coming out of S by the conservation laws. If we want to show that this equals to the cut value, what do we need to show? If you kind of just match terms, do pattern matching of terms, we know the cut values is some of the capacities going from A to B, right? So we can write the capacities. And I'll write it in the same notation so you can see. Right? So what needs to happen for that flow to be equal to that cut value? If you just look at these terms, what do you think needs to happen? Anyone? Yeah?
The F star from U to B needs to be equal to the capacity, and the subtracting terms need to be 0.
Okay, so the claim is that if we sort of eyeball this in pattern match, we want that first term, which is summed over the same things as this, to be equal to this, and we want the second term to be 0. That's sort of one way to make sure these two things are equal. Okay? And in fact, that's exactly what we're going to show. We're going to show that first term equals this term, and the second term is 0. Okay? And we're going to do it term by term. We're going to show for every particular UV edge going from A to B, this happens. Okay? So here's the argument. So case 1. Okay? Suppose F star U to V is less than C U to V. So obviously it can't be more, right? But if it's not equal, it might be less than. Okay? What is going to happen? Let's look at this more carefully. Let's draw a picture here. So we have U and we have V. Okay? And the flow on UV is less than the capacity. In the residual graph, what does this edge look like? If I had to write down the residual graph version of this edge after pushing F star flow through it, what is it going to look like? We've pushed F star flow forward, right? And we've got F star coming backward. So it's going to look like this. It's really going to look like do you agree? Because you pushed F star flow through the edge, the transformation to the residual graph will say that, okay, you have the forward edge, which is now of effective capacity C minus F star, and the back edge has capacity F star. Is that correct? Yes? But now we have a problem. Can anyone see the problem? This is in our final graph. This is what this edge UV now looks like in the final graph, where we've constructed this cut. What is the problem? Yeah?
Is it doesn't push F star more flow?
Well, we don't know if we could push F star more flow, because we don't know what else is going on. But you're on the right track. Your intuition is correct, but the statement you're making is not directly verifiable. There's a different statement that you could make that is in fact true and will cause us problems. Yeah?
In fact, the algorithm has not stopped, or there is a path between U to V.
Remember what we claimed. We claimed that A was the set of all vertices reachable from S. We don't know if there's a path from S to T. But if this is the case, then our assumption is wrong because we said V was not in A. We started off with this graph saying V is not in A, V is in B. But now we're saying, no, in fact there's an edge from U to V. That means V is reachable from S. Right? Because U is reachable from S, and therefore V is reachable from S. There is a contradiction. And this contradiction has happened precisely because F was less than C UV. That's why there was this leftover edge there. And therefore, this cannot happen. So this is a contradiction. Does that make sense? So what we're saying is, if there was an edge from A to B that was not fully saturated, that had flow on it that was not as equal to its capacity, then you could actually reach that edge, that vertex V that you said was not in your set in the first place. So this cannot happen. So all vertices going forward are fully saturated. That's the first part of what we want to show. The second part, of course, of what we want to show is that the second term up there, the subtraction term, is 0. And we're going to show it pretty much the same way, term by term. So let's look at this case now. So again, case 2. Again, U belongs to A and V belongs to B. Suppose F star V to U, so there's a real edge, is greater than 0. What does that mean? Well, let's draw an edge. There's an edge from V to U. So this is V, this is U, as before. And there's an edge from V to U. And this is flow F star. We don't know its capacities, but its flow is F star in it. That means that we must have a back edge with capacity F star. Because we just pushed F star flow on it. There has to be a backwards edge to change our mind. But what did we just say? This means that now V is again reachable from S. And we get another contradiction. Therefore, all forward edges are saturated, all backward edges are empty. The flow going out of A equals to the cut value, and max flow is equal to mid cut. And that's your proof. One second. Yeah.
So which means like we choose set such that there are only forward edges.
No, we just said what's reachable. So we said we'll define a cut. We have to produce a cut. Using our flow, we'll construct a cut that matches it nicely. We didn't just come up with this cut by magic. We looked at the flow value to put.
We haven't discussed how this algorithm works here, right?
We have. Find an augmenting path,
Yeah.
augment, repeat till you stop. That's exactly the algorithm. We haven't discussed how long it takes. So that's what you're asking. Any questions? So this is the proof of correctness that this algorithm in fact works and gives you the optimal solution, V max flow. Okay? It also, as a byproduct, proves that max flow is equal to min cut. Or it proves that max flow is equal to min cut as a byproduct using algorithm, whichever one you think is more important. But we have not said anything yet about how long it takes to. And that's going to be the next question. But before I go on, I want to make sure that's clear. All right. So it's with this kind of algorithm, or with any iterative algorithm that says keep doing something till something happens, you first have to make sure that the something you want to happen will in fact happen, that it will actually stop eventually. Right? If you're saying keep running till the stopping condition is true, you better make sure your stopping condition is true before you worry about other things. So let us assume that the capacities are in fact from E to the integers, not the real numbers. Yeah, assume the integer capacities. So in particular, the capacity is either 0 or 1 or 2 or 3. Under that condition, we can prove that it stops in a finite number of steps. And it's not that hard to see this without even, to write it down. So if the capacities are all integers, can we show that this will always stop? Imagine what you're doing at every step. You got to.
I think like each time you increase, you push something. So at the end, you must reach the limit.
Pardon me?
You must reach some limit.
Is there a limit?
So if you set each edge capacity to 1, then
No, but edges have arbitrary capacities.
theoretically it says infinite and
No. But can you? I mean, yes, theoretically. I mean, what I don't mean. Is there a limit you can express in terms of the input?
with the size of the graph, some more capacity.
Sum of all the capacities in the graph. Why is that? Oh, sorry. You are correct. I asked you if there's a limit. There is a limit. There are two things though. You want a limit. Okay, so in other words, the claim that Pavel is making is that there is a limit on how much flow you can have in the graph. What's the total capacity of the graph? Maximum value. He says it's a sum of all the capacities in the graph. You can do slightly better than that actually. In fact, you can say that the maximum, the cut size, the min cut, right, is less than equal to the sum of all the capacities coming out of the source, right? So if you look at the source, and you have one edge coming out that's say got capacity 10, another 20, 50, and so on, you know that the min cut has to be less than equal to 80, right? Because that's total capacity coming out of the source. You can't have any more than that. Right? Okay.
You can do the same with sink.
You could do the same with sink. Exactly. You can take the min of the two things. But having a limit is not enough. So you all know the story of Zeno's paradox and the hare that's trying to get to the carrot. The carrot is 2 units away, right? But it takes an infinite number of steps to get there, right? And that's not a good thing. So every step it jumps, it covers half the distance between itself and the carrot, but it gets tired. So next step it's half more, and so on. So you need one more thing to make sure this algorithm converges, along with having a limit. What is the other thing you need? So if I want to get from there to there, I want to make sure I eventually get there. What do I need to be sure of? Or what is sufficient for me? If I'm walking, yes?
It's sufficient that you push at least, you push 1 unit flow.
Or I take a step that's big enough. If I take a step that's reasonably big, that's at least something, I know eventually I'll get to the end. If the hare always jumped, some small fraction of distance, you would always get to the end. The problem in Zeno's paradox is that it's jumping, a vanishingly small amount of distance in the limit. Can we be sure here that we're always pushing a certain amount of flow at every step? What do people think? Can we guarantee this? That there's always some amount of flow being pushed? There's a lower bound, in other words. We can always say the flow we push in any step is at least something. Yes?
So any path will have a capacity, if it's non-zero, it must be 1.
Any path from source to sink, if you look at the minimum capacity, so let's take a path from source to sink in the residual graph, right? So we have source, we have some edges, and we have the sink. And let's look at the minimum capacity edge here. Remember that all capacities are integers. And when we subtract flow, they remain integers. So the min capacity, if it's not 0, has to be at least 1. Because these are all integers. You see this? Yes? That since the capacities are integers, and you're only ever adding and subtracting integers when you push flow, you will always have capacity 0, in which case there wasn't a path in the first place, or at least 1. So if you can push flow, you push at least 1 unit of flow. We just said there's a limit on the total amount of, each unit of flow contributes to that overall capacity buffer. So you will eventually stop. Okay, so augmenting path increases flow by greater than or equal to 1 unit. Which tells you immediately what the running time of this algorithm is going to be. What is it going to be? So the running time of the Ford-Fulkerson algorithm is going to be the time to find a path. So it's going to be less than or equal to time to find a path times the number of paths. We just said this is a BFS, so this takes time m, which is linear on the size of the graph, right? And we just said the number of paths, let's call it C star, which is equal to the sum of all the capacity coming out of the source. Let's say it's source. So the running time of Ford-Fulkerson is right? Because we guaranteed it converges in the other way. Yes? Yeah.
So on a computer, even if we did use real numbers, since we have finite precision, would it still be guaranteed to stop at some point?
As long as your numbers are as long as there's a lower bound on the amount of flow you push, which in a finite precision world will be true, yes, you will stop. There is one problem with this algorithm. It's not a polynomial time algorithm. Do we see why? Why is this not a polynomial time algorithm?
It's the same problem as the bandits with knapsacks. It's dependent on the value.
And not the size. To write down the capacities takes size logarithmic in their value, but my running time depends on the actual value. And if you think this is a very crude upper bound, and there's no way this can actually happen, there's a very simple example I can give you. So let's say you have a source here. Let's say I have a graph that looks like this, and these are my capacities. What is the max flow in this graph? 2000? Yes? What's the capacity coming out of the source? Okay, so C star is 2000, F star is 2000. This should run in 2 units, 2 steps, right? First step, 1000, 1000. Second step, 1000, 1000, we're done. But what could happen? For some reason unbeknownst to us, because we didn't tell Ford-Fulkerson how to complete their augmenting path, they might decide to go this way. How much flow would it push? How much flow would that augmenting path push? If you go from S, let me label these things. If I go from S to A to B to T, how much flow can you push along that path? Why? Because this is the bottleneck. So you push 1 unit along that path. What happens to the residual in the residual graph, that edge from A to B? It flips direction, doesn't it? Because the downward direction becomes saturated, but the upward direction gets a capacity of 1. Okay, the next step I go from S to B to A to T. How much flow can I push? 1. What does the edge now look like? Oh, it's back to looking downwards again, A to B. It's flipped back. You could imagine the algorithm going, boom, 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 boom. How many steps would it take? It would take 2000 steps, which is exactly what the algorithm says. Now, you of course will protest loudly. It's like, this is ridiculous. You should not do this. But I didn't tell it not to do this. I didn't tell the Ford-Fulkerson algorithm, hey, be smart about your paths. I just said, find any path. Yes?
So what if we say find the biggest path?
I'm glad you brought that up. I'm going to talk about that just in a second. When you say, wait, what's biggest?
The path with the most
Flow?
flow?
Okay, hold that thought.
Okay.
In about 2 minutes we'll get back. Maybe 3 or 4. So, even though the analysis looks very crude, there are examples where, without any further constraints on the algorithm, it could actually do this. So you have to be wary of this algorithm. And there is one more problem. I said that the capacity should be integers. And that if they're real numbers, I can't prove what I want to prove. Why? Because I can no longer guarantee that I make progress towards my goal. It might take a long time to make progress if I'm doing fractional amounts of flow at every step if I have real value. You might also say, well, yes, it'll take long, but that's the problem with real numbers. You know, what are you going to do? Life stuff. But it'll still eventually get there. Finite precision and all that stuff. There's an example in notes that I encourage you to look at. It's an example where the capacities are not integers. The algorithm could take a series of paths, an infinitely long set of paths, and it will converge to a value that is wrong. So it's not even that it takes infinite time to get the right answer, it takes infinite time and gets the wrong answer. And not only does it not get the right answer, it gets the wrong answer and it gets it spectacularly badly. In other words, you can construct, and you should look at this example, it's a very cool example in the notes. And basically this example allows you to say that. And they don't even have to be real numbers. Just assume they're irrational. So you don't need fancy transcendental numbers. So there exists a graph and an execution such that the value of the flow is 2x plus 1, again look at the notes, for any value, for some value x that you specify when you input the graph. And the value given by Ford-Fulkerson is less than 7. Regardless of what x is. You can make x a billion. The Ford-Fulkerson number will give the answer 7. Well, actually a number less than 7. Because of irrational values. So it's not even that the irrational values cause you to take infinite time. They can cause you to take infinite time and get the wrong answer. So these assumptions are very important. The integer assumption. And yes, finite precision is essentially integer at some lower level of precision. So. But this still means the running time is bad. You know, even if you do all those integer assumptions, the running time is still bad. And the question is, what are we going to do? Okay. And it turns out that there's one of those cases where a greedy strategy actually works quite well. In fact, there are 2 greedy strategies that work. And we're going to talk about them next. Let's take a 3-minute break. Yeah?
For irrational numbers, can we do like a threshold, like we...
Do what you want with that. I mean, you want to get that answer. You want to, so then you don't know how far you are from the wrong answer. Suppose your capacity is irrational. Even figuring out whether a sum of rounded numbers is close, you don't know. I have a quick question for all of you. How many of you actually are, I'm just curious, how many of you are going and looking at the videos, the class videos after the class, just to go back and check things? Just a show of hands. I'm just trying to get a sense of how much it is. Okay, that's a reasonable fraction. I mean, also since, there are not 84 people sitting in this room right now, I imagine many of you are watching the videos solely as well. How many of you have, just decided not to come to class and watch the video instead? No shame here, just asking. On any particular day, of course you're here now, so by definition, yeah. And was that helpful? I mean, when you missed the class and watched the video, was it, almost as good as the real thing? Or was it, in other words, was it able to see everything and follow everything there? Or, okay. There are many ways you can fix the Ford-Fulkerson algorithm to make it run in polynomial time. There are many other algorithms you can also design that will run in polynomial time. In fact, there's a huge body of work on this topic, and it's quite current. The best bound, I think, is about 3 years old. So even though these things came up in the 1950s, till this day people are trying to improve the bound. And I think the best bound now, the bottom line, so, and again this is in the notes, so the best bound, and this is not based on Ford-Fulkerson, is O of M n, which is about, close to the best you might imagine getting. If you're willing to be randomized, you can do a little better. If you just want the value of the flow, you can do a little better. But this is a pretty good bound. We're not going to get that bound today. But we are going to show you how to convert the Ford-Fulkerson algorithm into one that actually runs in polynomial time. We're going to do it in 2 different ways, using a greedy strategy in both cases. And they just have different greedy strategies. First one, we'll call fat pipes, which is your strategy. The second one, we'll call short pipes. Both of these methods will give you a better bound for the Ford-Fulkerson algorithm, but they're dependent on the parameters in slightly different ways. And one is not always better than the other. In fact, there are cases when the Ford-Fulkerson by itself is the best of the 3 of them. So depending on your situation and the kind of graph you're dealing with, one of these 3 methods might be the best thing you want. Okay, on that note, when would Ford-Fulkerson be a good algorithm? Well, when would it not be a bad algorithm? What's making it bad? Yes?
Well, if all the capacities were the same in the graph.
Well, same is not enough, I think. Well, if they're the same, yes, you can then scale them, I guess, is what you're thinking. Is that what you're thinking?
Maybe.
Okay. Well, if they're all the same, you can then pretend they're all 1.
Yeah.
And at that point, well, even that is not quite. Well, yeah, if they're all the same, you can pretend they're all 1, I think. And then but in general, I think the idea is that if the capacities are all small, or the total capacity coming from the source is small, it's not a big number, then there's nothing wrong with the Ford-Fulkerson. Only when the capacities become very big, you have a problem. You want to be able to show someone you can make faster progress. The problem with Ford-Fulkerson is it makes very slow progress. You want to be able to make faster progress in some form. And so these methods are ways to get you faster progress. The first approach is called what we'll call fat pipes, which basically says both of these are just ways of choosing an augmenting path. They don't change anything else about the algorithm. So the analysis and the correctness all work the same way as before. So fat pipes basically says pick the augmenting path that maximizes flow. Right? So in that example we had with the 2000 thing, what would happen here? It would say, okay, there are 4 paths I could take. I could go SAT, SBT, SA, or 3 paths, SABT. These are 3 paths I could take. The first 2 have a flow potential of 1000. The second one is a flow potential of 1. Third one is a flow potential of 1. I will take one of the first 2. So you take the SAT, you get 1000. And then SBT is the next one, you take 1000 you're done. So intuitively this makes sense, right? If you want to make progress, grab as much flow as you can. Right? Don't waste time on little paths. It's not difficult to find such a path. It's not a straightforward BFS anymore. But you can think about how you might go about finding such a path of maximum flow value. It relates to finding a spanning tree, and I won't say any more. You can think about that for But the point is that its running time is similar to running time for amino acid, so it takes n log n time. But how do you now show that this actually converges faster than the Ford-Fulkerson algorithm does? And the key is, of course, that it's greedy. It's taking something that's just grabbing a lot of flow in one step, and somebody want to use that fact to help us. We want to somehow say that you make a lot of progress. And so let's consider that you've picked a particular path. Okay, so let's look at the proof that fat pipe will actually converge in a reasonable amount of time. So let's say we pick a path of value, so flow value, let's call it V, say. Okay, and we're pushing flow on. What can we say about how much this relates to the overall flow in the graph? Well, let us now look at a particular cut. Okay? So consider, so let A be equal to all vertices reachable from S via edges of capacity greater than V. Okay? I claim that A and its complement are an ST cut. Why is that? So A comma why is this an ST cut in this graph right now? Remember my assumption. I picked the path along which I had maximum flow. That was the point of picking this path, right? It maximized the amount of flow I could push through. So why is this statement now true? Anyone? Why is, so what do I have to show to prove that A, V minus A is an ST cut? What do I need to show here? Yeah?
All the edges reaching T are less than V, less than equals to V. Actually,
Well, what is the definition of an ST cut?
T should be separate.
T should not be an A.
Yeah, exactly.
How do we, can we prove that T is not an A? What is A?
All edges.
So why can't T be in that set? Why can't T be in the set of all vertices reachable from S by edges of capacity strictly more than V? Remember what V is. What is V? V is the maximum value I was able to push along a path from S to T. Suppose T is in A, then there is a path from S to T along which every edge has residual capacity more than V. Why am I not pushing along that path? I can't push along the path because I just said that the maximum flow I could push was V. So there's no way T could be an A. Because if T was an A, that would not be the maximum value. Does this make sense? I feel like maybe this is a little confusing. So I assumed that the max value I could push from S to T was V. So if I look at the edges that have the capacity more than V in this residual graph, they can't contain T as well, because otherwise I would have pushed it. So this is an ST cut. Okay, what's the capacity of this cut? Remember, the capacity of this cut consists of all edges going from A to V minus A. Each of those edges must have capacity less than V, by definition, because it's not reachable anymore, right? So therefore, we can say that the capacity because there are at most E edges between A and V minus A. Each of them has capacity which is less than equal to V. So just this was. Okay. Now we want to say that if we're pushing a value v, the flow value v, so we know, for example, that since this is, we know that the flow value star is less than equal to m times v, right? Because the flow is less than the cut and the cut is less than mv. But let's flip this around. This means that v is greater than equal to f star divided by. Okay, it's just a rearrangement of inequality. But what does this say now? Again, don't look at this as just an inequality. We're saying that v is the amount of flow we just pushed. And we're saying it's greater than or equal to f star over m. In other words, it's reasonably large. We are, by saying that we want to push the maximum flow possible along an augmenting path, we are guaranteeing that the value of this flow is a reasonable fraction of f star. It's a 1 over m fraction. Right? So in other words, once we push this, the residual flow left in the residual graph is going to be what? So after pushing v, the flow, max flow in residual graph is equal to f star minus v, which is equal to f star 1 minus 1 over m. If you think of m as a number that does not change as the algorithm runs, we are saying that we have reduced the flow by some fixed factor after one iteration. Now think back to recurrences. Think back to all you learned about recurrence analysis, or you want to forget how you learned about recurrence analysis, or divide and conquer and so on. If I tell you there's a process that after one step reduces to some fraction of itself, what does that say about the process? It's going to terminate in a certain number of steps, isn't it? Because at every step you pull off a constant factor. This is not a constant in the traditional sense, but it's a constant in the sense that it's independent of the flow value itself. It just depends on m, which does not change in the graph. In fact, if m decreases because you effectively destroy a bunch of edges, that only gets better for you. So because the flow in one step, by pushing the maximum flow, reduces by this factor, we can say, after k steps, the remaining flow that you need to capture, f star is, let's say k, is less than equal to f star times 1 minus 1 over m to the k. So we've already taken off a certain amount of flow. This is what's left. So we need to still find with this algorithm. When will this stop? When this number goes down to 1. Once you get to a constant, then you can just peel them off one by one. It doesn't really matter. At the point, regular Ford focus can take over. So when is f star times 1 minus m to the k is equal to 1? That happens when 1 minus 1 over m to the k is equal to 1 over f star. Now if you remember your secret weapon here, that 1 plus x to the 1 over x is roughly equal to e. Now this is in the limit as x goes to 0, this is equal to e. You can rewrite this as 1 minus 1 over m to the m times k over m is equal to 1 over f star, which gives me e to the minus k over m should be equal to f star to the minus 1. Right? If you take logs on both sides, you end up with something like, what do you end up with? What is the value of k here? So you get minus k over m is equal to minus log f, right? And so what you get is k is equal to m log f star. I already said that one iteration of this algorithm takes roughly m log n time. So the running time of fat pipes takes m log m, which is the time to find one path, times k, which is equal to O of m squared log m log f star. And again, the log versus ln doesn't really matter that much, it's a constant. This in fact is polynomial time. Why is this polynomial time when the previous one wasn't? This also has the value f star in it, right, which relates to the capacities. But why is this polynomial time? Because I'm taking the log of that value. That in fact is a polynomial of reason. So just by saying we want to grab as much flow as we can get a better problem. Any questions? Yes.
Isn't m still exponential in the input?
M is the number of edges.
Oh, sorry. Okay.
Yes.
Is there no way to do better than the n log n term?
If you take this exact algorithm, no. But you can do better by changing the algorithm, of course. There are many other things you can do. You have to find this max bottleneck path, essentially. And I'm not sure there's any other way to do it except by the minimum spanning tree. Basically what you're doing is you're finding a spanning tree that connects the source and the sink of max bottleneck or min value, and that tells you what the value is. Otherwise, yeah. Or use like or something.
So, didn't you tell us that finding the min cut of a graph is NP hard or NP?
Nope, I did not.
You did not?
I did not. In fact, I gave you an algorithm for computing in n squared time randomly. Into the fourth. And I just, so no. The problem that is NP hard is the max cut, not the min cut. There are a lot of problems where minimizing is easy, maximizing is hard, or vice versa. Yeah. Min cut is easy, max cut is NP hard. Shortest path is easy, longest path is NP hard. And there are other problems. Any questions on this? Before I move on to the other pipes? Okay. The other algorithm is a different one, which is called short pipes. And as you can imagine, it modifies Ford-Fulkerson in the obvious way. Not the one that carries the most flow, but the shortest one. Again, you can find this using a BFS. So finding such a path is easy, it takes m time. The only question is again, how many times you have to keep doing this. And again, if you think of our example, that bad path was a length 3, the good ones are a length 2, so it will work even in that case. You take So when I say find the shortest path, I mean find the shortest outgoing path, then look at the flow you can push along and input, as always. Okay? So again, the question now is, can we show that this process terminates in a reasonable amount of time? Now this proof is a little bit more tricky. It's not, well, I won't say the other one is not tricky, but this one is a little bit more involved because you have to make a reason, you have to reason about sort of progress at every step, just like we did before, but it's a more distributed kind of progress. In particular, so let's say that I've done, let me get my notation right here. So let's say you've done I such paths, okay? So after I paths, we have some residual graph. So after I steps, we have a graph GI, right? And let Fi be the current flow. So G0 is the original graph, F0 is equal to 0, and then after some number of steps, you have Gk, and Fk is the final optimal flow. And our goal is to figure out what k is. Right? So you do one step, you augment it. What we want to define is a notion we'll call the level of a vertex in I. So let me do the next page. The level in the ith stage of vertex I is equal to the distance from S to V in GI. Okay? So what is so initially, hopefully the sink has some level. It's a distance, the shortest path from S to T is some number. When the graph stops, when the algorithm stops, what is the level of T going to be? It's going to be infinity. If you can't reach it, let's call it infinity. Right? So in the beginning, in G0, right, the level of T is equal to the distance from source to sink, whatever it is. And by the time you get to the end, we know by definition, because it's the end, the level of T will be infinity. Because you can't reach it anymore. If you could reach it, then it would still be pushing flow. So the level of T will go from something and it will increase. Right? You can sort of see that it might start increasing. And the key point is that you can show that for any vertex in the graph, its level increases with time. And the way to visualize this, to understand what this is saying, is that it's saying that if you take the initial graph and measure distances to vertices, and you start pushing flow through them, what's going to happen? Eventually, you're going to push as much flow as possible through a vertex, and that edge is going to get reversed. That means you can no longer get to it now. Right? Maybe you saturate its capacity. So the path to get to that vertex now will get a little longer. And what this claim is saying is that this in fact happens for every vertex. Every vertex level never decreases. Things only look like they're getting further and further and further away. And at some point, of course, T goes infinitely. And that's when you stop. So this claim is trying to capture this process of level increase that's happening in the graph as you start pushing flow through it. Now you can actually prove this fact. This is proven in the notes. And this is proven by induction on I. So you look at a path of length, on the length of the path. For any particular level, you look at the length of the path, and on induction length of the path, you can show this. So the inductive hypothesis is that for a path of length k, it's true, then look at a path of length k plus 1, and so on. And it's just a bunch of inequalities that you play with to get this. But the key thing is that because the levels increase, you can say something a little bit stronger. And that allows you to say something about how edges behave in the graph. So, let's consider a particular edge. So now let's look at, so this is a claim. I'm not going to prove this, but this is again the notes. Just remember this claim. Okay. So now consider any edge you're going to be. Okay? So think of what's going to happen to this edge as you push flow in the graph. So you're pushing some flow through it, you're pushing some flow through it. At some point you push as much as flow through it as its capacity. What happens to this edge? It flips direction. Remember that graph we saw, that edge was flipping direction after you saturated it? Right, so you keep pushing flow through it, and suddenly it now looks like this. But now you might continue pushing flow and you change your mind, right? Oh no, I push flow backwards, and at some point you push more flow through it, and it goes back to this again. Then you push some more flow through it, and it might go back to this again. It flips its direction. Right? We don't count flipping direction unless it actually fully flips. If it's got a bit of flow going forward, backward, that's not counted as a flip. During the course of the algorithm, this could happen to every edge. It could flip. The insight that comes from this analysis is that this edge does not flip very often. No edge can flip very often. If it flips once, it flips twice, that's it's done. Suppose I told you that in this graph, during the course of this algorithm, every edge flips at most once. Can you say something about the number of steps this algorithm must take? Okay, so here's the question again, think about this. I tell you that an edge flips completely. That means it saturates and flips the other way. Only once. It's not true, but let's say it flips only once in the whole course of the algorithm. We know it's not true because in the example that one capacity edge was flipping back and forth over and over again. But let's pretend it's true. Okay? Can we say something about the running time of this algorithm? Yes?
It would be at least bounded by the number of edges because...
At least or at most?
Or at most, yeah. So...
Explain.
Because every path you take, you flip at least one of those edges.
Why do you flip at least one edge?
Because there's one edge that's the bottleneck.
That's the bottleneck.
When you flip.
Exactly. So you flip one edge, you do one flip operation every time you run an augmenting path. And if I'm telling you that no edge can be flipped more than once, the total budget of flipping that I have, the flipping budget is E, is a number of edges, right? So I can only do that many flips before I have to be done. My budget for flipping is over. So if in fact every edge flipped exactly once, I could give an immediate bound on how many iterations this algorithm would take. This is what is called a potential argument. The number of flips is like a potential energy, and you could withdraw from that bank, if you wish, every time you actually do an augmenting path. And at some point you'll run out of energy, you can't do any more. But of course this is not true. I lied. I mean, it's not true that every edge flips only once. But here's what you can say. Now that you've accepted the premise that bounding number of flips is a good thing, so I just argued that if I can give some kind of upper bound on the number of flips, I have created an upper bound on my flipping budget. Since every augmenting path withdraws at least one from that budget to flip, I will have an upper bound on the overall algorithm running time. I am claiming this fact here. This is not the budget I wanted, but it's a budget. Because now, what is the flipping budget? Right? So let's say V is equal to N. Okay? I said each iteration itself takes, M time, because I'm finding the shortest path. I'm just finding and I can do BFS for that. So this would imply that the running time is equal to the time per iteration times which has no dependence on the total flow value. So it's in some sense even nicer. It's what is called a purely combinatorial upper bound. It does not depend on actual values of the flows or capacities or anything. It just depends on the structure of the graph, or just on the size of the graph. Of course, I have not yet proven this claim. But let me at least say that if this claim is true, if I can somehow show that this edge does not flip too many times, I get a bound. So do you see the reasoning here again? Again, I'm saying that I have a budget for the number of times an edge can change its direction. I put an upper bound on that, that gives me an upper bound on the total 20 times. Because every augmenting path must flip at least one edge, the bottleneck edge. Otherwise this analysis would work. If I couldn't prove that, if I couldn't make that claim, this whole thing would break. But because I know that every augmenting path flips at least one edge, and I know I have a budget on flipping, I'm done. It's a more generalized version of the basic forward focus analysis. There's something that happens at least once every step. There's a budget on the total number of steps. All that's left to show is that each edge flips at most 0 times. And again, the proof is in the notes, so I'm not going to prove it completely, but I will tell you the thing that allows me to prove that. Okay? The thing that allows me to prove that is the following claim. Let's look at an edge UV. This is at level, let's say this is at level I in the graph. Let's assume that at GI plus 1, it goes away. So now this edge is gone. So now you only have UV here. And let's say at some stage J, you again have UV coming back again. So you have UV, it goes away for a while, and it comes back at level J. Okay? Let's say this happens in my graph. Then the claim is that the level of I, or level of J, of U is greater than or equal to the level So what I'm saying is that an edge shows up, it disappears, and it comes back. As soon as it comes back, the level of U has increased by 2. Why is this important? What is the range of values a level can have? The level, remember, of a vertex is the shortest path distance from the source to that vertex. This is an unweighted graph. The distance can be 0, 1, 2, 3, 4, up to n, or v. There can only be as many vertices on the path as the number of vertices in the graph. And after that, it goes to infinity. So if you think of the trajectory, if you think of a number line here, so let's draw a number line here. A very bad number line. Starting at 0, this is infinity, and this is n. What we're seeing is that every time it flips, it jumps by 2. Then it flips again, and it jumps by 2. Then it flips and it jumps by 2. And it flips and it jumps by 2. At some point, it reaches n. If it flips after that, it goes straight to infinity. Oops. So how many times can the edge flip? Well, it can flip at most n over 2 times. Because if you believe this claim, then every time it flips, its level has increased by 2. Its level can be no more than n before it goes to infinity. So therefore, the flipping, therefore UV flips less than or equal to n over 2 times. Now, of course, all I did was replace one claim, which was this one, by another claim, which is this one. Luckily, this claim is a little bit easier to show just by using the fact that levels always increase. Once you know levels always increase, it's a very simple case analysis, again, which is in the notes, that shows you this fact. Once you have this fact, you can prove this fact. And once you have that fact, you prove the overall. And again, these are I brought it down to the level, hopefully, where the proofs themselves are relatively straightforward. And so I've given you the idea of how to think about the proof. The rest of it is just calculations. And again, please do read the notes to look at it. So just in the last minute that we have left, or 3 minutes we have left, let me summarize. So we have the basic Ford Fulkerson, which we'll call it vanilla, which takes time, m times c. We have Ford Fulkerson fat pipes, which takes time, what was it? M squared log m log f star. And then we had Ford Fulkerson short pipes, which is, and as you can see, they're not easily comparable, right? M times C, if C is very small, as I said before, the first one is great. So if C is a constant, that takes M time, these are much worse. So there are cases when the capacities are small, that Ford Fulkerson is actually a good choice for you, the vanilla version. If, for example, the total flow in the graph is likely to be small, then the second one is pretty good. The capacities are big, but because of structural bottlenecks, the flow is going to be small. The second one is quite nice. If you can't give any good bounds on the capacities in the flow, then the third one might be a reasonable solution. So it all depends. And again, there are many, many more nodes to the point where now, like I said, we're at the point now where we can basically get this, which is clearly better than all of these except the vanilla one and except when C is very small. It is better than all of these things. Mn is always better than m squared, because m is at least n for a practical. And you can do much better if you're willing to just get the value of the flow. You can get down to n if you want to get just the value of the flow, even slightly better, but that's another story. So that's where things stand. And in what follows in this class, we are not going to go any more in depth into flow algorithms. We're going to take these things as black boxes. And for the rest of the lectures that we talk about, I'm going to talk about how to apply flow to solve problems. And then the assumptions that you take a problem, map it to a flow problem, just apply whatever algorithm you want. So we won't say any more about algorithms to compute flow. Yes?
For the short pipes, can you actually construct a graph where every edge does split B over 2 times?
I don't know if it's tight. It would be a little tricky. I'm not sure.
What's the one you saw, the worst case one?
That one there, but only one edge. But that's not, but then in that case you won't even do the flipping because you'll just take the short paths. You'll take 2 short paths and you'll be done. So in that case, with that edge that was flipping, you were actually taking the not short spots to get that flip to happen. It was illustrating the flip idea, but it wasn't really, you wouldn't get that with the sound.
Okay.
So it's not clear how you'd construct something. I mean, again,
I'm just wondering if it's possible to.
I don't know. These things are hard usually. And also, it doesn't have to flip n over 2 times. You could flip n over 10 times, it would still be the same kind of bound. Right? As long as there's some large enough number of times, you'll get this bound, m squared. But I'm not sure. Yeah. You'd probably want something where you have all capacities of 1 and you have a bunch of things that kind of, you have a weird graph that looks like 2 edges, 2 edges, 2 edges, 2 edges, so you keep flipping and you keep